Okay, let's start it. Yeah. So this is the course of 8201, the theoretical module. And my name is Chen, Department of Physics, and I will be lecturing this part of the lecture, this part of the course. Uh, uh, so the content of this part is about the path integral and its application in physics. Yeah, path integral is a very interesting and very important theoretical tool and methods that were initiated by the great theoretical physicist, American theoretical physicist Richard Feynman in the end of I think in the end of 1940s, right after the Second World War, and has many applications in both in high energy physics, statistical physics, quantum mechanics, and even in stock market and any other physical related fields. So so everything related to this theoretical module will be taught in this week until the week of 13th. And in this course, so we'll just discuss the method and path integral in quantum mechanics, in statistical physics, and even in quantum field theory, right? So is there any questions here? So if you have problems, if you have questions about my teaching or about the content, please feel free to raise it, or you can write on the chat box. Is that clear? Is that clear? Is that clear?
She says yes.
Okay. So you can hear me, right? You can hear me. Can you hear me well? So I assume you can hear me well. Okay. Yeah. Okay. So the reference of this what's the reference? There are several very nice, very important books about path integrals. So the first would be the classical book by Richard Feynman himself, and Hibbs. I guess Hibbs was his graduate student, and they have a book of quantum mechanics and path integral, which is the first one here, right? There is a cheaper reprint from Dora. It's about, I think, about 10 US dollars, something like that. Yeah. So you can also download it online. There's some, I'm pretty sure there is a online PDF version of this classical book. So the second reference book would be the path integral in quantum mechanics, in statistics, and in polymer physics, and in financial market. This is a book written by Hagen Kleinert, right? This is also a very comprehensive book in this field, and you can learn many different topics. Yeah. So the third one is a French authored book by Jean Justin. He's a field theorist, and The title of the book is Path Integrals in Quantum Mechanics by Oxford, preprint. So the first one is condensed matter field theory, which I may refer to this book often in the course. This is a famous book by Alexander Ortland and Ben Simons, and printed by University of Cambridge publisher. And there's also online version if you can find. There's a third version of this book. The last one is quantum field theory and condensed matter, an introduction by Shankar. Shankar is a faculty at is a professor of physics at Yale University in United States. Yeah, he has written many good books. So that's about performance. So 2 to 3 homework will be assigned during this course, and then the final grades will be based on the homework and the attendance. And the last homework will probably wait a little bit more. I guess it will be a little bit more than the first 1 or 2 homework. So yeah. So lecture 1. This is today's lecture. It will be Feynman path integral. Yeah. So what is the? You have question? Is there a question here? Okay, if there's no question, let me continue. So what's the origin of path integral? Part of the motivation was actually started from Dirac, the great British scientist Dirac. So around that time, people try to extend classical physics to quantum mechanics, and in Schrödinger equation or in Dirac equation, they all use so-called Hamiltonian. They treat the Hamiltonian, they quantize Hamiltonian. Originally Hamiltonian is a classical object. Then they use operator to replace the variables in the Hamiltonian. So then they can solve non-relativistic Schrödinger equation and the relativistic Dirac equation and obtain the wave function of the electrons. So Feynman at that time was asking the question. So in classical physics, in classical mechanics, both Hamiltonian and Lagrangian are treated equally. They have the same kind of usage in classical physics and classical mechanics. However, in quantum mechanics, before Feynman, so only Hamiltonian is widely used, but the Lagrangian is not, right? So Lagrangian is not. So then his motivation is, can one formulate, quantum mechanics from Lagrangian instead of Hamiltonian? And he looked up into Dirac's book, and Dirac, in a paper by Dirac, I think in 1920 or 1930s, he actually, stated, some propagation of a particle is the action is somehow related to the Lagrangian, but he did not expand the discussion. So Feynman was inspired, and he proposed the formulation of quantum mechanics in terms of path integral. Yeah, let's see how things works here. Let's go through what Feynman thought and did in his very nice paper in the 1940s, and see how he formulated quantum mechanics in terms of path integral and in terms of Lagrangian. Yeah, in terms of Lagrangian. Yeah. So we turn to the path integrals that was first studied by Richard Feynman in his treatment of one particle, one free particle in one spatial dimension. So in one spatial dimension whose coordinate, whose position runs from minus infinity to positive infinity, for which the resolution of that identity is this. What does this mean? If you have learned quantum mechanics, so if you integrate out all these Hilbert space, which here is the Hilbert space is spanned by position. So this is this is equal to identity. So this is the resolution of identity. So we first review the real time case and quickly go through the imaginary time case. So don't worry about this real time or imaginary time. If you understand one, you can understand the other, right? So we'll consider a relative path integral based on another resolution of identity. So we'll emphasize h bar, the Planck constant h bar, since the Feynman approach has so much to say about the classical limit. So in the classical limit, so h bar goes to 0. So except for the fact that the Hilbert space is infinite dimension, the game plan is the same, right? You chalk up the potential to chalk up this ut into a product of n factor. This is the time evolution operator. Yeah, by chopping into this n times, the time interval from 0 to t, we cut them into n pieces and insert the resolution of identity and take this n pieces into infinity, right? So we are trying to understand how this particle in one spatial dimension evolve as time goes, and this ut is the evolution operator of the state of the particle, right? So the Feynman's path integral in real time. Yeah, let's see how things works. So let's start from the Hamiltonian. Let's assume the Hamiltonian for this one particle is independent of time, is time independent. Has this expression, which is p squared over 2m plus the potential experienced by this particle, right? This can describe electron moving in one dimension, or whatever particle is moving in one dimension, right? First of all, it is evident that one can write this exponential, which is the evolution of evolution operator, unitary time evolution operator, which is exponential I time times Hamiltonian divided by h bar. And because we're working with infinitesimal amount of time, which is epsilon, this epsilon is infinitesimal amount of time. So this describes the evolution of the state of the particle after during the infinitesimal amount of time epsilon, right? So E minus I epsilon divided by h bar times this Hamiltonian. Because this epsilon is very, very tiny, one can expand this exponential into two pieces, right? Exponential this part, the first part, times multiplies exponential I epsilon divided by h bar times the potential energy. If I'm strict, if I try to be strict enough, this cannot be an equal sign. This is an approximate sign. This is approximate, right? The reason is that this potential and this kinetic energy P squared by 2m is the kinetic energy of the particle, and the potential energy of the particle, they do not commute. P, the position, the momentum operator P and the position operator X, they do not commute. They do not commute. This, in more precise terms, this expression, exponential, a plus b, this part plus b part, they cannot equal to this exponential a, exponential b. There is an actual commutation relation here. Look at this. This is the precise equation. Exponential a times exponential b is not equal to exponential a plus b because a and b do not commute, right? It is equal to this 1/2 exponential a and b commutate plus more high order terms, right? But because this part is epsilon small, this part is also epsilon small. The reason we ignore the commutation relation between this and this is because the commutation between this and this is order of epsilon square, right? Because of this is epsilon square, and both this one, if I call this A, if I call this B, this is order of epsilon, this is order of epsilon, and this is order epsilon square. So then, because epsilon is very tiny, extremely tiny, in the limit, epsilon goes to 0, and this thing is of high order, so it has to be vanished. So if I chose epsilon to be extremely small, then this commutation term, the commutated term just vanish. So then this approximate sign can be thought of as equal sign, right? Like if I think this as A and this as B, A and B, the commutation relation between A and B is of high order, is of epsilon square. And because epsilon square is vanished, so we do not need to worry about this commutator here, right? So it is clearly more delicate for operator which could have larger or even singular matrix element. So we will simply assume that in the limit epsilon goes to 0, this equal sign, this approximate become equal sign, right? So now we want to compute. Is there a question here? Is there a question? Let's see. If you have a question, please feel free to interrupt. Yeah. So we want to compute the time evolution of the system from state, x, in position here space, to a final time, where the system evolved to x prime. And this thing is called probability. But this is square, this amplitude square is equal to the probability for the particle propagating from position x to position x prime, right? With the Hamiltonian, with this governed by this Hamiltonian, right? During the time interval of t. And this ut over n is equal to u times epsilon, because we divided the time interval t into m pieces, and each piece is epsilon, divided by h bar, right? So in order to evaluate this probability or this probability matrix element, we need to compute this this object, right? So what we can do here? So to do this, let's consider let's illustrate the outcome by considering n equals 3, where there is three of these this object times together, three of this, n equals 3, n times epsilon, and 3 times epsilon is the time. So what we do is we have three of these exponential minus epsilon p squared time multiple exponential I epsilon times v, and we have three of them together. What we are doing is to insert the solution of identity, and we insert two of them, insert this resolution identity of this one, which is the integration of dx1. I insert the resolution identity dx2, which is this one. So then things will become clear. So this step, people clear. We insert this resolution of identity, which is this one, this resolution identity. This thing equal to 1, so we can always insert this one, right? We can insert this part, which is 1, and this part is equal to 1, right? Right? So so this part equal to 1, this part also equal to 1. So then let's evaluate this matrix element, because each of them is identical, almost similar to each other. If we understand one of them, the whole thing will be clear, right? So the rightmost exponential operator, so this operator, right? Because this thing and this thing do not commute, and this thing is exponential minus potential act on the position. This is the origin operator of this. When this act on that, you just replace the operator x with this position x n minus 1 and put this thing out, right? This become a number. But x, the state x, the bracket variable x, is not the origin operator, origin state of the momentum. It is not. How do I evaluate this matrix element, right? So the essential question is how to evaluate this question, this object, right? Is that clear? So this is the most difficult part. We need to evaluate the matrix element of exponential I epsilon 2m h bar p squared with respect to two position eigenstate. So this is the eigenstate of the position, but we are evaluating momentum, right? So this come to the exercise, which I would like you to do as a homework to evaluate it. So the way to do it is to insert the identity operation, identity resolution of identity here in the momentum space. You introduce bra p times bra p, bracket p, and integration over p, and then this act on momentum equal to momentum, and then you just need to figure out how does x and p, what's the magic element of x and p. So this is given as a homework, which is clear as here. So you insert the resolution identity, which is this one, into this part, into this part, and this act on that, you can become a C number, become a complex number, and you can pull out of the metric element, and this operator act on this momentum and become a C number, become a complex number, and you can pull it out. So then the thing is become evaluating the metric element between the position and the momentum. Yeah. So then this object is, after doing some integration of the momentum, become this thing, become this object. Is that clear? Let me pause for 1 minute to hear your question here. Can you have any questions? You can raise it up right now.
We have another student here.
Yeah. You have a question here?
Do you have questions? Oh, okay.
Yeah, so this part of the lecture, I'm essentially following the book by Shankar, Quantum Field Theory and Condensed Matter. Actually, I would like to lecture on the whiteboard, on blackboard, because this lecture is better to be delivered in blackboard fashion with derivations rather than just using PPT, use PowerPoint, and it is probably more efficient if I use PPT. Use Blackboard instead of PPT. Yeah. So for the student who missed the beginning of part, so this is a lecture about path integrals, and path integral was invented by the great theoretical physicist great theoretical physicist Richard Feynman, and he tried to, one of the motivation he had is to treat the Lagrangian and Hamiltonian on equal footing in the generalization of classical physics into quantum mechanics, because around his time, only Hamiltonian was emphasized in quantum mechanics. Lagrangian was not. Right? He tried to figure out whether there is a way to rely on Lagrangian instead of Hamiltonian to formulate quantum mechanics. And he learned that Dirac had a paper describing that. And then he systematically generalized and extended Dirac's result into path integrals, and he invented the concept and the method of path integral. So path integral is a great method that has been applied into many different contexts of condensed field physics, including quantum mechanics, statistical physics, and the quantum field theory, and even in stock market, in some polymer physics, etc. Yeah, there are reference books here. There are many of them, including the classical book by Richard Feynman. So I will probably rely mostly on this Shankar's book and and Simon's book, and also probably the book by Kleinert on path integral in quantum mechanics and statistics and polymer physics. So this is really a fun subject. Path integral is a rather exciting and a fun subject. So I encourage you to do the read some of these books and with some care. I think it's a very exciting theoretical tools and method, and carry some beauty, carry some level of beauty. Is the theoretical formulation and the underlying ideas and the structure of the symmetry and anything else that can be buried into this simple, interesting formulation of path integrals. Okay. Yeah. So here we are trying to compute the propagator, the probability in one dimension, a particle moving from position x to position x prime during the time interval t, and with the under the evolution operator under the Hamiltonian governed by this free particle Hamiltonian, which is time independent, only has a kinetic energy and the potential energy, and this is the propagation operator or time evolution operator. There are different terms of it. This is called time evolution operator during the time interval epsilon, because we are separating this time interval t into n slices, n pieces, each piece equal to t divided by n, right? Right. Yeah. So we have to compute this object. So to compute this whole thing, we only need to evaluate one piece of it, or one or two pieces of it. So here we try to evaluate 3 pieces of it, but 3 matrix elements or 3 pieces are of the same structure, of the similar structure. So if we understand one of them, the remaining 2 are clearly no. So to evaluate one of them, which is this object. So because P and X do not commute, capital P, capital X are both operator. They are operator. The reason we express them into capital letter is because they are operators. They are not they're not a C variable. So this is a C variable. This bracket labels the state of the particle, and the eigenstate is in terms of the position, position operator, right? So to obtain this object is to insert, the identity resolution of identity of in terms of momentum, because this momentum do not commute with x, and this x is not the eigenstate of P, right? So consider now the remaining metric element. It is simply the free particle propagator from xn minus 1 to x in time epsilon, right? So this is the exercise I would like you to do in the homework. So I will submit the homework on the module, or share you with the emails, and to let you to carry out the homeworks. Yeah. So let's see. So after replacing this metric element with this result, so you found the question here. Is there a question? Okay. So we found this time u is the time evolution operation, which is exponential IH times t divided by h bar, right? This is the operator, but we are expressing its metric element from position x0 to xn, x0 to xn during the time period t, right? So if we gather this result, right? Because this is a n pieces of it, and we have the piece being computed to be this form. So the whole thing is this, right? So if we rewrite, so we'll gather this into this form. So this can be this exponential thing, which is this is nothing but the momentum. But let's do some simple manipulation of it. Let's pull out this IH bar, I divided by H bar, times the time interval epsilon, right? This is I divided by H bar times epsilon, and the summation over this object, right? Summation of this object. Right. So what is that? What is this? What is this? Yeah. So this is xn divided by minus xn minus 1 divided by epsilon is nothing but the momentum. It is the definition of momentum. If you have learned the quantum mechanics, if you learn the calculus, the limit of x n minus x minus 1 divided by the time difference in the limit of time difference goes to 0. That's defined as the derivative of x over time, right? So this is nothing but x dot. This is the this is the calculus we have learned, right? So this is m times the velocity divided by 2 minus the potential energy. This object is nothing but a Lagrangian. This is Lagrangian. Yeah, this is Lagrangian. Yeah. So this actually was obtained by Dirac, but in the 1930s. So Feynman was inspired of that and formulate path integral from that. So this is Lagrangian. Yeah. So because we have this integration of all these intermediate positions, right? We are doing integration over all positions, all intermediate positions, and this is replaced by this is labeled by this Cooley math Cooley dx, right? So exponential IH bar times the Lagrangian, right? And this mass Cooley is equal to this expression. So now this is the familiar Lagrangian, which is the kinetic energy divided minus the potential energy. So the continuum notation, this is the continuum notation, is a schematic for the discretization version of this discrete version of this continuum version, right? This is the path. This is in the path integral, right? So what does that mean, right? So that means the propagation probability or the evolution probability from x to x prime during time t. We need to integrate all possible paths, all kinds of possible paths from x to xp, any kind of paths, and the weight or the probability for each path is given by this object, exponential IH bar time Lagrangian, right? So the weight is given by that, right? So this is the essence of quantum mechanics. All possible paths are possible, but the probability weight is different, and the weight is measured by Lagrangian, right? Is measured by Lagrangian, right? So this is the essence of quantum mechanics. And when Feynman expanded his path integral idea, in the 1949 days, I think in 1949 or 1948, there was an international conference. So Feynman was formulating path integrals and tried to apply to quantum electrodynamics. And Niels Bohr was in the audience. Is the question? Oh, there's no question. Don't worry. So Niels Bohr was in the audience. Niels Bohr was at the time was a leader of quantum mechanics. He was in the audience, and he refused to accept the idea of path integrals, and he thinks quantum mechanics has no path. There's no so-called path in quantum mechanics, and he said, he like Richard Feynman does not understand quantum mechanics. He should go back and learn quantum mechanics. For this reason, Feynman was not awarded the Nobel Prize until the death of Niels Bohr, when Bohr passed away. So the Nobel Prize committee eventually awarded Nobel Prize to the inventor of quantum electrodynamics. Yeah. So this is the part of the history when the new concept was refused by rather senior people in the field. Yeah. Yeah, but nowadays path integral is a very powerful, very widely used technique in field theory, in many other fields. Yeah. Okay. Yeah. So let's continue. So the quantity, which is the integration of the Lagrangian along the time path, which is the time integration of the Lagrangian over the path xt, is the action of the path, t. Because there are all possible paths is any kind of path is allowed, but the weight is given by exponential IH bar times this action, right? Apparently, this is a function. What functional? What is functional mean? So functional means it's a function of a function, right? So this thing depends on the path. So this Lagrangian integration over time depends on the path of xt. The position, the path is a function of time, right? So that means the action is a functional. It's a function of function. It's a function of function. The variable of this function is a function. The variable is the function itself, right? So functional means it's a function of function. Yeah. Okay. So we may write the path integral schematically as this. This is how Feynman manages to express the quantum mechanical amplitude to go from the position x to x prime in a time t as a sum of a paths with equal unimodular weight for every classical path connecting the endpoint in space-time. So why then does the world look classical? The answer is that as we sum over all crazy paths, the rapid oscillating exponential cancel out until we approach a path for which the action is extremal, right? So because there are all kinds of possible paths, but the h bar is very small. So then any deviation of the path will generate a different phase factor, and they will cancel each other. So in the end, all the extremal path become more important, right? So that S remain nearly constant and the unimodule number add up into phases into something sizable. So this extremal path is called is a classical path. So let's see how eventually see how in the path integral formulation how quantum mechanics and classical physics are related to each other. Yeah. Let's look at this evolution operator, time evolution operator once more. So this is integration of all possible paths, right? And this is exponential over exponential of the Lagrangian, evaluated along a particular path, right? The physical meaning has been stated. Yeah. Okay. Okay, let's take a maybe 10 minutes break. So we'll come back at 5:30. Okay.
Hi, Professor Chen.
Yeah, what's up? What's up?
Yeah, I came late for 15 minutes and I registered in this model.
Oh, that's fine. That's fine.
Okay, thank you.
Don't worry. Let's get restarted. Let's get restarted. So yeah, so we have expanded the physical meaning of path integral and path integration. So which is that? So the evolution operator or the evolution probability from position x to x prime during the time period of t is given by the integration of all possible paths, which is written as big curly T dx, and weighted by the exponential action. This is the action, which is given by integration over the Lagrangian. Yeah. So all possible paths is allowed, and they have different weights, right? And because of this smallness of the Planck constant h bar, the many passes, many contributions of the different passes, they cancel out. These weights are rapidly oscillation. The phases are rapidly oscillation. There are a lot of cancellation. So in the end, all the extremal parties survive, or many times extremal parties survive. Yeah. So what is extremal parties? Extremal parties is given by the Euler-Lagrangian equation. So they obey Euler, or I think it's read as Euler-Lagrangian equation. So which is this object? Yeah. Euler-Lagrangian equation. So partial dx, d over dx dt, the partial Lagrangian over partial x dot equal to partial Lagrangian over partial x. Remember, this is total derivative d dx, and this is called the principle of least action. And this equation is obtained by finding the extremal of this function. You try to obtain the largest dominant value of that. Yeah. Okay. So path that contribute coherently must have action within the roughly h bar of the action of the classical path. So outside this region, the path cancels out. So in a limit, when h bar goes to 0, so we may then forget all but the classical path and its coherent neighbor, right? So in the limit h goes to 0, what does h equal to 0 mean? H equal to 0 means classical limit, when the system reduced to classical path. So in this limit, one can choose a one path, which is the path given by the classical path, and then this thing just becomes exponential I over h times the s classical, become s classical. This is the classical path, right? And this classical path is nothing but the solution of this is Euler-Lagrangian equation. This Euler-Lagrangian equation is the classical equation of motion. So if you write down this, express this equation, this is nothing but F equal to ma. This is just F equal to ma. How to see it? This is the class which defines the classical motion, defines the classical path of the particle moving in one dimension under the potential Vx, right? How to see it? So the Lagrangian L, partial Lagrangian partial x dot. This is nothing but m times x dot, m times the velocity, right? Then you take another total judicial time. This becomes m times lx double dot, right? M times x double dot. X double dot is acceleration, So m times a, right? What's the right hand side? Right hand side is partial Lagrangian versus partial x. Lagrangian partial Lagrangian partial x is nothing but the v times vx partial v partial x and the minus sign. This is nothing but the force experienced on the particle, right? So this is nothing but F equal to ma, right? So parts that contribute coherently must have an action within roughly h bar of the action of the classical path, right? So this is the classical path. So in the limit h equal to 0, which is the classical limit, one focuses on the exponential factors and pay little attention to the amplitude, pay less attention to the amplitude, right? There is a way, with some work, one can calculate the amplitude by systematically include the fluctuations around this classical path. This is called the semi-classical approximation. So it works only because h bar actually tends to 0, but because we are interested in a particle that is getting so macroscopic that any tiny change in its path causes a huge change in the action measured by h bar. Right. So there are many problems where the answer is the sum of all configurations, and there is a number, which is the counterpart of 1 over h bar in front of the corresponding action that is very large, allowing one to replace the sum over configurations by contribution from the stationary point of the action. So these are also called the semi-classical or saddle point approximation, right? So if one replaces 1 over h bar with some big number, because h is very small, so 1 over h is a large number. If one has the action, there is a prefactor of some number in front, which is very large. One can do a saddle point approximation and replace the sum over configuration by the contribution from the stationary point S, right? So the preceding treatment rely on the fact that the complex exponential behave like a real one in that its main contribution comes from where the action is stationary. It is a mathematical fact that a rapidly oscillating exponential is as bad as a rapidly falling one, right? So when we go to imaginary time part integral, things will become a lot simpler. We'll be working with a real exponential, right, which is predominated by the minima of the Euclidean action for obvious reason, right? When in a complex time, this has absorbed and this become a real exponential. Okay. I think this part need to be learned by yourself. So this is a toy model to doing this saddle point approximation, to perform this saddle point approximation and try to compute both the amplitude and also the saddle point action. On the other hand, one can also try to compute the fluctuation, the higher order term that has been ignored in the saddle point approximation, right? So alpha is a big number, so you expand around the minima, and to quadratic order, then is higher order terms has been thrown away, And if you include the higher order terms, and how does this higher order terms scale in this center point approximation? So this is what you can work out in homework. So
Excuse me, Professor.
yeah, the question.
Yes. Could you go to previous page? Well, I mean, if the action S is imaginary, what does it mean? What's the physical meaning of it?
Physical meaning of what?
Of action S is imaginary number.
Action as an imaginary number. What? Well, I don't. Can you be more precise? I just didn't get your question well.
I'm wondering why action S can be an imaginary number or a complex number.
Why is a complex number? Yeah.
Yes.
So this is a yeah. Depends on how. Yeah. So if I try to be short, if my answer is try to be short. So in your time evolution for the when you write down your Schrödinger equation with time, so then is a minus h bar partial t per side equal to h times h per side, right? RH bar partial t. So in the time evolution, there is an imaginary I in front of it, right? So the imaginary I tells you the time evolution of the wave function of the particle of the Schrödinger equation. So contains the imaginary part that will become the I here. So this is the Hamiltonian, right? This is the evolution operator, right?
Yes.
Yeah. So that explains why we have imaginary part. If I try to be long, if my answer is try to be long, so there was a creation by Schrödinger. So in the initial formulation of quantum mechanics, he tried to think what should we put in front of this time evolution, and in his final version by Schrödinger, when he come up with the final result for Schrödinger equation, he put I in front. He put the imaginary number. So this imaginary number is a creation. It's an important creation. So the first factor, this first factor. So complex number, complex I was a mathematical invention, right? I is I squared equal to -1. So I is square root of -1. So I is a mathematical invention. How does this mathematical invention enter into physics, right? Was a development by theoretical physicists. One tried to relate the complexness of this I, the first factor, into quantum mechanics, try to understand the time evolution as well as interference phenomena. Because we think of particle, the real particle, as a wave object, we try to use wave mechanics, wave package to describe the time evolution, describe the propagation of a particle. So we end up with the first factor. With the first factor, one can understand the interference phenomena, right? Understand diffraction and interference. So that's why we need to put the I in front of the Schrödinger equation when Schrödinger come up with the Schrödinger equation, right? So there is a deeper reason, the historical reason or deep physical reason why one need the I in quantum mechanics. And the quantum mechanics, according to some great physicists, probably the most important development of quantum mechanics is the phase, is the first factor, is the phase. Is not a quanta, it's the first factor. So the most important the essential part of quantum mechanics is not quantum, and is a phase factor, and this is the thought by Xin and Yang. Yeah. So the phase factor, it turns out to be more fundamental than quanta. Yeah.
Okay.
Yeah,
Got
this is
that.
what he thinks. Xian Yang, Chen Yang, he thought the phase factor is probably more important, more crucial for quantum mechanics than the concept of quanta.
Okay.
Okay. Yeah, so let's go to Feynman's first space path integral. So in last part, there was a path integral in real space, or in configuration space, if you like. It's called configuration space or position space, or simply path integral. This is a path in real space, path in the position, or path in the configuration. More generically, path integral can be defined in any kind of Hilbert space, right? In physical Hilbert space, right?
Yes.
Yeah. Well, if you accept the configuration space is one example of Hilbert space, which is a position X, right? Okay.
Okay.
So now we consider another one. Let's go back to this stuff. This is basically U X naught X N and T, right? This describes the propagation and the evolution from position X naught to position X N during the time period T, right? Yeah. So let's now introduce the resolution of identity between every exponential and the next. So we need two versions. One is this identity, resolution of identity in terms of configuration, and the resolution identity in terms of momentum. Where the plane wave states have a wave function given by this. Yeah. Yeah. So this is nothing but a plane wave. You know, this is the eigen state of momentum, and if you write down its wave function, it's just a plane wave whose momentum is a fixed number, is p, right? This is a plane wave function. Yeah. So let's first consider the case of three time intervals, right? 3 time intervals. N equals 3. So this gives us that, you know, we insert both the position and the momentum. So you act the exponential, the potential energy on the X, because this capital X is operator. It acts on X equal to X. So you can, this become a C number, you can put it out. And this is the momentum. Momentum, you act on momentum, this become P squared, and you pull it out. So then and this is the path in the phase space. Both momentum and position are being integrated, right? So this becomes d capital, you know, this dp dx, right, with this path. So when n equal to 3, so evaluating all matrix elements of the exponential operator, is trivial since each operator can act on the eigenstate to its right and get replaced by its eigenvalue. This is just become a C number. You can depend whether they act on left and the right. Just choose. You can choose the right eigen operator, right? So this act on right. This act on right. You can point it out. Become a C number. So then you accumulate gather this exponential part together, and this becomes partial dip dx exponential. This is Pn squared plus minus this kinetic potential in this term. Where this term come from, right? So this is come from here. So you pull this out. This become P2 x1, and this is the exponential minus PA times x divided by h bar, exponential P2 times x1 divided by h bar. And this you pull this thing out, this become x1 bracket P1. This become exponential RA x1 times P1 divided by h bar, right? So you put them together, this become exponential RA h bar. So P x1 minus P2 times minus P2 plus P1, yeah. So this is contributed to this term if you get them correctly. So this is called the barrier phase term, but then don't worry about this at this stage, yeah. So this become that, yeah. So in a limit, when n goes to infinity and epsilon become infinitesimal small, we write down schematically in continuous time the following continuum version, which is this I divided by h bar 0 to t p times x dot minus h dt, right? So this Hamiltonian and now written as a function of continuous variable t. So this is called the first space path integral, where the path is defined in the first space given by x and p, right? Right. The continuum version is very pretty, right? But it's only schematic for this discretized version preceding it, right? In our problem, since p enters the Hamiltonian quadratically, it is possible to integrate out all n variable Pn. Right? You can integrate out the p because p is a simple integral because it's rather simple. This is linear in p. This is quadratic in p. So this you can do a Gauss integration. This become a Gauss integration. So once you perform the integration over momentum, you obtain this object, right? This object. This is nothing but the result for configuration path integral we have done before, right? Right. So yeah, so this is after integration over the intermediate p, right? Yeah. So now we now bring into the configuration integration. We find that this gives us exactly the configuration space path integral as it should. Right? Yeah. So that's the configuration path integral. Generally, any kind of Hilbert space you can invent can be used as a basis for path integral. You just find the appropriate basis for your problem. Yeah. 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 Let me pause for 2 minutes. Let you to digest this this part. All right, let's continue. For the last part. Let's see. Let's see the path integral for imaginary time. Yeah. What does imaginary time mean? So imaginary time is rather simple. We just replace the IT minus IT with the question. We replace the minus IT with the imaginary time tau. Yeah. Yeah. So we can write down a path integral for it, following exactly the same step. Is there a question? No question. A quick question.
No, please continue.
Yeah. Yeah, so imaginary time is a little bit easier to work with, to deal with, instead of the imaginary time. So we can write down the path integral for it, following exactly the same step for the real time. The final answer in continuum notation is of this kind of form, where now epsilon equal to, instead of t, now we use tau, and the Lagrangian is become this plus that. So this is called the Euclidean Lagrangian, and it's like a Hamiltonian because this is plus sign instead of minus sign. The reason why it's become plus sign is because when you write down t equal to I tau, this is I squared, then is a minus sign. So we pull the minus sign out, this become a plus sign. Yeah. Yeah. So yeah, thus a particle obeying the Euclidean equation of motion will see the potential turn upside down. This will be explored later. Let's don't worry about it. The Euclidean action, though, is defined likewise as the integration of Euclidean Lagrangian and the imaginary time tau. Yeah. So we emphasize. We have emphasized that the continuum form of the path integral is a shorthand for the discrete version. It is true here also, but overall, the path integral, the Euclidean is the best behaved, rapidly varying path with a large kinetic energy surpassed by the falling exponential factor. So the extremal action now become the smallest action. You find the extremal action now is to find the smallest action because of this minus sign here. It's not complex anymore. Yeah. So now we try to think the classical quantum connection, how to establish the question. Yeah, let's just continue with try to figure out the classical quantum connection. So we see that in order to have the right limit in the continuum time, the classical Ising model must have its parameter in special tau continuum regime, such as this h bar equal to epsilon. We want to derive similar condition on the parameter of a classical model where the fluctuation variable is continuous and can take any real value. Right. consider a classical system with n+1 sites and a degree of freedom xn at each site. A concrete example is one-dimensional crystal where the atom labeled n is located at Na plus xn. Na is the equilibrium position and xn is the deviation from it. So the variable at the end of the chain is x naught, xn fixed. So then the x. Got a question? Yeah. So the action is integration of a path and exponential 1/kt. So in statistical physics, we replace the we have exponential minus beta h. Beta is 1/kbt. K is the Boltzmann constant. We use this as a weight for the probability of a particular state, and the z is called action. It's a weight. It's a summation of all possible weights that contributed to this partition function. And from partition function, one can evaluate many other physical quantities. Yeah. So where E is the energy function, and we have written beta in terms of the more familiar temperature variable, beta equal to 1/kBt. So the reason for neglecting kinetic energy is for kinetic energy basically is it become roughly a number. It can be found in this problem. So the energy divided by kT is has this part, which is the separation between these and the deviation of that. So one can ask if we include this p squared over 2m into the Boltzmann weight, and this is called the Boltzmann weight. So when we learn statistical physics, we have this the probability for finding particle in this particular state is given by the weight, a weight, and its weight is e2 minus beta h. Yeah. Okay, so then one can compute the imaginary time Feynman path integral from x naught to xn for the time period of tau. Yeah. So this is the, yeah. Yeah, so the Feynman path integral from x naught to xn is identical in the form to a classical partition function for a system of n+1 coordinate xn with the boundary condition that the first and last at ax plus x and xn, the variable xn are interpreted as intermediate state labeled of the quantum problem in the repeated resolution of identity, and as the classical variable summed over in the partition function. So the role of Euclidean action in the Feynman integral is played by the energy in the partition function instead of the Lagrangian. So the role in quantum mechanics, the role of h bar is played by the temperature. So what does that mean? So when h is a small number, and right, t is the temperature. So there is correspondence of h and t. So in the classical expansion, when expanding around the classical path h, classical path and the start of fluctuation, one can do that. Similarly, one can do a low temperature expansion in terms of temperature, right? In particular, either variable goes to 0, the sum of all configurations is dominated by minimum action, or energy and fluctuation are suppressed, right? So the parameter in the classical and the quantum problem can be mapped into each other, right? So in the tau continuum limit with very strong coupling K1 between the variable in the neighboring time and a very weak coefficient for the term at a given time. Since epsilon goes to 0 in the quantum problem, the parameter of the classical problem must take some limited value to be really be in correspondence with the quantum problem with the continuum time evolution generated by the Hamiltonian. The single quantum degrees of freedom is treated for one-dimensional area of classical degrees of freedom. This is a general feature. The dimensionality goes up by one as we go from the quantum to the classical problem. For example, in one-dimensional area of quantum oscillation, quantum oscillators would map onto the partition function of two-dimensional area of classical variable. So this will probably discuss the later. Let me for the remaining maybe 10 minutes, let me just sketch some thought, which is very interesting. And I may come back to that in the next lecture. See how to think between quantum mechanics and the classical mechanics from this path integral point of view. And this is actually more important I think it's more important, and it has application in many different places. And we'll probably raise some concept called instantons. So we now consider application of Euclidean formalism. We have seen how the path integral can be approximated by the contribution from the classical path in the h equal to 0 limit, h bar equal to 0 limit. This procedure does not work for tunneling amplitude across the barrier, since we cannot find a classical path that goes over the barrier. On the other hand, in the Euclidean dynamics, the potential is turned upside down, and what is forbidden in Minkowski space is suddenly allowed in Euclidean region. Let's consider a potential in a double well potential. What does double well means? Double well means this is like this is the position, this is the potential, and this needs two minima. So if you have a particle either in classical limit, in the classical physics, the particle either being here or here, right? Either be sitting here or sitting here. But in quantum mechanics, yes, there can be tunneling event between two of them. So it's no longer here or here, it's a superposition of here or here, right? In this quantum mechanics, there is a tunneling event because this potential is not infinite. This barrier is not infinite. There is always tunneling, quantum tunneling from here to here, right? So yes, so you cannot ignore it. And this tunneling thing is called instanton. And path integral is a great method to evaluate this tunneling event or tunneling probability or the physics related to this. So this is the potential. It has two classical limits, so called plus a minus a, which is plus a minus a plus a, right?
Okay.
Yeah. So yeah, so in the semi-classical approximation, we have plus or minus a, but in quantum mechanics, we need a tunneling between them. These two states are degenerate with the same energy. You know, the Hilbert space is two. There are two states. The ground state has two states that are degenerate. So one is at plus a in the configuration space, or the other is minus a. But they are off diagonal matrix element. So this is plus a, this is minus a. But the plus a and the minus a, they have mixing. This mixing is the tunneling event, tunneling amplitude, or tunneling amplitude from plus a state to minus a state, right? So this tunneling thing is can be evaluated by instantons, and this tunneling which is off diagonal term, So how do we do it? So this totally is from minus a to plus a. This is the evolution operation, time evolution operation during the time period tau. The propagation from minus a to a. These are actually equal to each other. So the at the lowest order approximation, you can do a Taylor expansion of this exponential. This become 1 minus 1 over h bar times tau times t times h, and this become that. If you know high order term, this is high order term, and this is magic element from the original Hamiltonian, physical Hamiltonian from here to here, right? So this is you can do this evaluation. Do this evaluation. This is non-zero. This is clearly non-zero. Yeah. So if you replace this Hamiltonian, and you can do this calculation, you can find out that this yeah, the classical part is given by this, and this is given by this form. Yeah. So this is the this is given by this classical action in the lowest order approximation, and that tells you the off diagonal term, which he labels as h plus minus. This off diagonal term is given by this this classical action, and because it's a 2 by 2 level system, two states, you can write down the Hamiltonian the ground state, which is a symmetric state, sometimes called bonding state, an anti-bonding state, anti-symmetrized state, and the energy is one is minus, the other is plus. So there is this deviation. Yeah. Okay. So this is the difference. Yeah. Maybe let me just pause here. Next lecture, I will write down, just do a blackboard teaching, and the homework problem is basically all this exercise in this chapter. I will put the PDF online, try to list all these homeworks, and it's rather practical, rather elementary. It's an elementary exercise, and if you have questions, please either email me or drop me by my office in next week. And I think that's pretty much today's lecture. And let me just pause for a couple of minutes. You have any questions here? So
Professor, could you please upload this lecture 1 PPT to Moodle?
Oh, sure. I will do it. And also we'll put the video online. Yeah. Okay. So more questions?
Our homework. Yeah, our homework today is all of the exercise in chapter 5, right?
Yeah, there's only 7 of them, and mostly I just practice exercise. So so these problems are rather straightforward for me, and I'm not sure whether it's difficult for you, but I think in the beginning it may take some time. And if you have difficulty, just drop me by. I would be very happy to go through some of them. Yeah, the ultimate goal of teaching is try to let you actually learn or understand something, right? Rather than make you feel difficult, right? So it just give you yeah, it's not trying to give you a hard time. It's to help you to understand the subject. And this subject is quite elegant and quite beautiful. So I wish to share this part of the experience with you, and you can learn something from it. Yeah.
Thank you.
Yeah. So any more questions?
Maybe could you please introduce your research a little bit?
Yeah. So today is probably too little bit late. Maybe you can ask my student and postdoc who are still there, and
Okay.
they can maybe better. At least some of the work, some of the research are performing with these guys. And although I'm doing a little bit more than being assigned to them, you can ask what my interest is. Yeah. Okay, let's just stop here. I need to figure out how to save this recording thing. Yeah, let's end it here. Thank you.
Thank you, Professor.
Yeah.